Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel.
Dear students, now we will study about optical fibers, one of the applications of total internal reflection. Transmitting the signals through optical fibers is possible due to the phenomenon of total internal reflection. Optical fibers consist of inner part called core and outer part called cladding or sleeving. The refractive index of the core must be higher than that of the cladding for total internal reflection to take place. The signals in the form of light is made to incident inside the core cladding boundary at an angle greater than the critical angle. Hence, it advances with repeated total internal reflections inside the optical fiber without undergoing any refraction. The light travels inside the core with no appreciable loss in the intensity of light as shown in the figure 6.28a. This is the optical fibers. While bending the optical fiber, it is done in such a way that the condition for total internal reflection is ensured every reflection inside the fiber as shown in this figure 6.28b. So here the core has a higher refractive index and the cladding that will have a lower refractive index. This is the cladding and this is the core. And here the rays of light will undergo total internal reflection. Now let us see what is acceptance angle in optical fibers. To ensure the critical angle incidence in the core cladding boundary inside the optical fiber, the light should be incident at a certain angle called acceptance angle at the end of the optical fiber while entering into it. It depends on the refractive indices of the core N2 cladding, N1 here and N2 here, and the outer medium N3. Assume that the light is incident at an angle called the acceptance angle IA at the outer medium core boundary at A as shown in 6.29a here. So here the refractive index of this is N1, that is for here at this place it is N2 and here it is N3. The critical angle for this is about IC and the acceptance angle is IA, and there will be an acceptance cone created here that is shown in this diagram. So here in this case the Snell's law in the product form can be written for this refraction at the point A, that is given by N3 sin A is sin IA equal to N1 sin RA. To have the total internal reflection inside the optical fiber, the angle of incidence at the core cladding interface at B should be at least the critical angle IC. The Snell's law in the product form that's given in the equation 6.19 for the refraction at the point B is given by N1 sin IC is equal to N2 sin 90 degrees. So N1 sin IC can be written as N2 as sin 90 equal to 1. Therefore, sin IC can be written as N2 by N1. The ratio of the refractive indices of the two different media. From the right angle triangle ABC, the critical angle IC can be written as 90 degrees minus RA, and therefore this equation can be written as sin 90 degrees minus RA equal to N2 by N1, or cos RA equal to N2 by N1. Since sin RA equal to root of 1 minus cos square RA, substituting for this cos RA, we can have this equation 6.41, and substituting this in the equation 6.37, we will get this equation 6.42. In further simplification, we can write this acceptance angle as IA equal to sin inverse of root of N1 square minus N2 square by N3 square. That's the equation 6.44. And if the outer medium is there, then this refractive index N3 will be equal to 1. And therefore, the acceptance angle IA can be written as IA equal to sin inverse of root of N1 square minus N2 square. That's the equation 6.45. And light can have any angle of incidence from 0 to IA with the normal at the end of the optical fiber forming a conical shape called acceptance cone, which is shown here. This is the acceptance cone like this. And therefore the Snell's law in this product form That is here this numerical aperture can be written as n3 sin IA. That's equation 6.42. And what is this numerical aperture A? That is n3 sin IA. That's called as numerical aperture of the optical fiber, and that's given by the expression n3 sin IA. That's equal to root of n square minus nt square. And for air, this equation n3 will be equal to 1, and therefore the numerical aperture will become this Na equal to sin IA, that's equal to root of n1 square minus nt square. Dear students, we are going to study about the applications of this total internal reflection. Already you have studied about the optic fiber and where it is being used. That is called an endoscope. What is an endoscope? An endoscope has a bundle of optical fibers, and that is an instrument used by doctors to see the inside of the patient's body. Endoscopes work on the phenomenon of total internal reflection. The optical fibers are inserted into the body through mouth, nose, or a special hole made in the body. Even operations could be carried out with the endoscope cables, which have the necessary instruments attached at their ends. So here it is mainly and largely used for finding out any defects in the stomach. So using this endoscope we can find out whether the stomach is affected. And next we are going to study about refraction in glass slab. When a ray of light enters a slab, it travels from rarer medium, that's air, to denser medium, that's glass. This results in deviation of the ray towards the normal. When the light ray leaves the slab, it travels from denser medium, that is glass, to rarer medium, that is air, resulting in deviation of the ray away from the normal. After the two refractions, the light ray emerges in the same direction as that of the incident ray on the glass slab with a lateral displacement or shift L. That is, there is no change in the direction of the ray, but the path of incident ray and the refracted ray are parallel to each other with a shift L, as shown in this diagram. So this is the incident ray, and it undergoes refraction, and again it emerges. But if there is no glass slab here, this ray will have traveled straight like this, but the emergent ray has been laterally shifted, and that is called the shift L. So this is how the refraction takes place in a glass slab. For studying about this refraction in a glass slab, let us consider a glass slab of thickness T and refractive index N kept in air medium. If the path of light is A, B, C, D, the refractions occur at 2 points B and C in the glass slab. The angle of incidence I and the angle of refraction R are measured with respect to the normal N, N1 and N2 are the 2 points B and C respectively. The lateral displacement L is the perpendicular distance CE drawn between the paths of the deviated light and undeviated light at the point C. So in the right angle triangle BCE, sin I minus R is equal to L by BC, and therefore BC equal to L by sin I minus R. In the right angle triangle BCL, cos R is equal to T by BC, and therefore BC equal to T by cos R, where this T is the thickness of the glass slab. So equating the equations 6.48 and 6.49, we have L by sin I minus R is equal to T by cos R. And after rearranging, we have this lateral shift L is given by T, the thickness of the glass slab, and sin I minus R by cos R. The lateral displacement depends upon two factors, and also here again three factors: the thickness of the slab, the angle of incidence, and the refractive index of the slab, which decides the angle of refraction. The thicker the slab, larger will be the lateral displacement, and for a thin slab, the displacement, that is the lateral displacement, will be lesser. Greater the angle of incidence, larger will be the lateral displacement, and higher the refractive index, larger will be the lateral displacement.